All right, so let's get started. Today's topic is link analysis. We'll pretty much continue to investigate the properties of the network and properties of the vertices of the network, but we'll just look at it a little bit from a different point of view. So we'll start again. I'll remind you about a few graph theoretic definitions. We'll need those properties today. We'll talk a little bit about web search engines, though the topic of the lecture is, of course, and of this course, is social network analysis, but this particular ranking algorithm actually came from web search. And we'll talk about those two algorithms, PageRank and HITS. And we'll look at the web as a graph and realize how those algorithms related to what we talked about last time. And I'll touch upon a little bit on how PageRank is used beyond the web. Okay, so a few words, just sort of reminders from the graph theory. One very, very important thing for us to remember when we start dealing with directed graphs, and today we'll work with directed graphs, is that when you're writing the matrix that corresponds to the graph, adjacency matrix that corresponds to the graph, and it says Aij, it is a connection that goes from the node I to node J. For example, if we look at the picture here, node 2, the central node, is connected to multiple nodes, nodes 13, 8, 9, 6, and in this row, there are a lot of non-zeros. At the same time, if we want to look at the edges or links that are coming into particular node, that will be in the columns. So, for example, if I look at the column number 1, there is only one non-zero element. It's right here, and so there is only one incoming edge for the node number 1. Here it is. It is from the node number 10. So the point here is, for the directed graph, the matrix is not symmetric, and so Aij is not equal to Agi, and transpose is not, of course, that means transpose is not equal to the matrix itself. So again, last time we did not pay any attention to this because we worked with symmetric matrices. We worked with undirected graphs, so it were not important. Aij was, for us, just a connection between I and J. Today, it is very important where is I and where is J. So there are several types of nodes that are special in directed graphs. And one type are so-called absorbing nodes, or sinks. These are zero-out degree nodes. So these are nodes that do not have any edges leaving them. Well, here, for example, a bunch of them, right? These are all absorbing nodes. There are also, they could be, actually, number 5 is not. So this is absorbing node, this is. But there are also source nodes. These are the nodes that have non-zero out degree, but zero in degree. So they are the sources. And we'll, a little later on, we'll see in what sense they're the sources. A couple more important definitions, and you probably had them in discrete analysis, but I'll just remind them. So graph is called strongly connected if every vertex is reachable from every other vertex. So this is very important for us today because for strongly connected graphs, things will go smoothly. We'll have to fix the graphs that are not strongly connected. Now, if the graph is not strongly connected, sometimes it could be divided into strongly connected components. And strongly connected components are those partitions of the graph, as partition of the graphs in the subgraphs that are strongly connected. Well, if we look at this picture, you realize that, for example, here, these 3 nodes you can get from any node to any other node. You can get from A to B, from B to E, from E to A. Well, the same true is right here. But for example, if you can get from node B to C, there is no way to get from C to B. So nodes B and C do not belong to the same strongly connected component, and this graph is not strongly connected. Well, in other words, in strongly connected graphs, there is always a path in each direction between any 2 pairs of vertices. Matrices that correspond to the graphs, that describe those graphs. If the graph is strongly connected, the matrix is called irreducible. So irreducible means you cannot reduce it, you cannot divide it into subblocks, and where every block will correspond to strongly connected component. Okay, so again, for us, strong connection is good. And just remember the difference in between just connected components, and strongly connected components. Another important point is the notion of graph periodicity. So the directed graph is called aperiodic if the greatest common divisor of the length of its cycles is 1. So in other words, there is no integer greater than 1 that divides the length of every cycle in a graph. Well, let's take a look at this. For example, on the left image, we have 2 cycles. So this is a 1 cycle, and has 1, 2, 3, 4, 5 nodes in it. And there is another one right here, just 1, 2, 3, 4, 5, 6 nodes. So the period of one cycle is 5, the period of another cycle is 6. There is no integer greater than 1 that divides the length of both cycles, and these are the only 2 cycles in the graph. So this graph is aperiodic. On the other hand, on the right-hand side, we see there are, well, a bunch of cycles in the graph. So there is a cycle here, and the period is 3, right? There is another cycle here, period is 3. There is one more cycle here, it's also 3. And there is a big cycle, which is 1, 2, 3, 4, 5, 6, okay? So the period for this graph is 3 and 6, right? So the greatest common divisor of the lengths of those cycles is 3. So this graph is periodic, and the period of the graph is 3. Okay. Now, if by whatever reason we do not want to have we do not want to have periodic graphs, we want to have aperiodic graphs. What can we do? Let's say we're looking on the right graph. What can we do to sort of fix this and make it aperiodic? What changes can we do to the graph? We can probably add some edge to it. So what kind of edge? Any ideas? All right, I either cannot hear you or you guys silent. One of two. Okay, well, I still cannot hear you, but at least you had a few seconds to think about this. So the idea would be, okay, well, since there are cycles here over period 3 and 6, well, one thing to do is we can introduce a cycle, such a cycle that the greatest common divisor of the cycles will be 1, okay? Well, one way to do it is, let's say, All right, let's make it like let's introduce a cycle of the size 4, right? So it's going to be, for example, 1, 2, 1, 2, 3, 4, right? So I can make this connection, and this way I introduced a new cycle which is of which of the size 4. Now my cycles are 3, 6, and 4, and the greatest common divisor is 1. So this graph will become aperiodic. There is actually an easier way to do this, though. The easiest way would be to say, okay, well, you know what? If I'm allowed to do this, of course, I can just add a cycle for any node. Now, this short cycle will instantly destroy periodicity of the graph. And the reason, again, what sort of periodicity? Periodicity it really means, if you start from one node, in how many steps you get to that node, right? And in what period you can get to that node. And if we add any cycle of size 1, it means you can get to any node. We can, for example, return to this node in 6 steps, or in 7 steps, or in 8 steps, or in 9 steps, or 10 steps, just by spending some time right there. So we need strong connectivity and aperiodicity because they're very important properties for what we want to compute later on today. If you don't remember those things, spend some time and look at this. Check out discrete math. Okay, so back to the topic of the lecture. The search, well, actually, the search engines probably started in the early 90s, in 1993, 1995. Google itself as a company started in 98, and at first it was an open source. It was a search engine at Stanford, and it started with Sergey Brin and Lawrence Page and Larry Page publishing a paper on that project that was called The Anatomy of Large-Scale Hypertextual Web Search Engine. It's kind of interesting that by that time, by 98, there has been already a few search engines out there. There were Altavista, there were WebCrawler, and a few more. And people were using them. It was something new and exciting. But at the same time, it became very clear early on that search engine, well, can bring fame and can bring money if you can fool them and let them, for example, show you paper for, show you page, web page for all kind of requests, search requests. And so Google, when it came out, it actually worked better in terms of the relevance, providing better search results than other search engines known at that time. And well, the legend is that this was due to the algorithm that Sergey and Larry introduced. And that algorithm was called PageRank. And well, it's an algorithm for ranking pages. Well, it also has the last name of one of the inventors. So what you see here is actually on the left is the way that the Google web page looked like when Google just started, and on the right, this is the diagram from their paper on the sort of the first architecture of Google. It's actually the first and the last diagram of Google architecture people have ever seen. Now, most of the search engines have pretty much the same sort of architecture. Now, of course, it's much more complicated and scalable, etc. But really, the idea is the same. Again, this class is not about search engines, but just sort of for you to guys be aware how this works. The idea is the following. So you have a crawler. And a crawler is an engine that goes out on the web, goes to certain URL and fetches the pages. So here we have the web, and crawler goes onto the web and collects web pages. And those web pages being stored and then being parsed and indexed. Index creates document index, which is index or create a document index that can be searchable by text. But also there is a process, and then here this block anchors, it actually extracts URLs, checks through URL resolver that those URLs do exist, and then extract links. And in fact, you within the search engine, well, you have on one hand indexer that has information about the text that that pages contains, but you also have a web graph, or a graph of the web pages and connections between pages that have been accumulated here in the links. And when the user comes in and does a search, sends a search request, so what happens? Well, first of all, information to the search comes from doc index that gives us documents that are relevant, meaning that those documents contain the search terms and they're weighted appropriately. But also there is this PageRank score, the score of the importance of the web page that comes from the web graph. And in fact, again, the legend says that this is the main component. This is the main differentiating factor. This is what made Google Google. And it could be very well true at the very beginning. Of course, other search engine caught up later on. But the idea is that before Google, most of the search engine were using links. We're using, of course, document index to provide relevant results. Plus, they sometimes use the in degree counter. So, counting how many other pages pointing to a particular page as a sort of proxy to the importance of the page. Well, Google introduced this entire metric, which they call PageRank, and supposedly that what made Google results much, much, much better. Just for curiosity, if you look here at the screenshot, it says 25 million pages. So that's how it all started. I think probably 10 years ago, they stopped publishing the size of the index when it exceeded billions and billions of pages. So, but anyway, this is sort of the generic architecture of the search engine. And it's clear that when the search engine goes out to the web, part of the process that happens is it creates a web graph or a snapshot of the pages and how those pages are interconnected by the links. And in this case, links are hyperlinks. Now, the reason we want to study that is because a hyperlink from one page to another page is really an implicit endorsement that is the author of the page A gives to the page B. So in some sense, it is very, very similar to the citations. If the paper is cited by other papers, well, that really is endorsement to the author of that paper by other authors who cite that paper. And so when people connect and when they point URLs from their web pages to web pages of other people, they implicitly endorse those people. Okay, and so pretty much the web graph is the graph of endorsements. Now, again, we're talking right now about this sort of the most primitive model without all kind of dynamically generated pages, etc., etc. But if you look at this, you realize that yes, probably here that there are there are pages like C that has one incoming link, but then there's page D and page B that have two incoming links. And one way to use this information to help ranking the importance of the page, if the page contains text that is relevant to your query, would be, of course, counting incoming links. But that can pose a lot of problems. Aside from just natural problems, there are issues with people trying to spam the engine, and it's very, very easy to spam. For example, let's say the user A, who created the web page A, want to increase its rank, and we're using incoming links as the factor in ranking. Well, what user A can do is create what's called link farm by just creating a bunch of other pages and pointing them to your page. And all of a sudden, the rank of the page A, if as a rank we're just using the incoming links, will increase. It seems like in late 90s, that was one of the ways spammers were increasing their score on the search engines. And so PageRank, in some sense, it wanted to, on the one hand, use this idea, this notion of importance based on the incoming links. On the other hand, take into account the fact that the pages that do endorsement, or the pages from which links are coming, can be very different. And so the endorsement from the page, like, let me clean this. From the page like A, from this page, should count less than the endorsement that, for example, comes from page D. And the reason being is nobody points to page A, but at the same time, page D has 2 incoming links to it. And so page D should be able to provide stronger endorsement than page A. So does it remind you about anything we talked before? Remember last lecture, we talked about centrality indices, cut centrality, the idea of prestige, when some person is important if there are other people pointing to it, and if those people are important in turn. So this is really the same idea, just expressed a little bit differently and expressed in terms of the web graph. It's interesting to note that nowhere in the original paper on the web graph there were any words about sociology or about those indices, about the ideas of the node centrality, node importance, or the notions of, say, rank or rank prestige. It's not clear if guys knew about those publications and that research, or if they didn't. The only thing they reference is the literature on bibliometric citation. So the notion that these pages is like citations, though they also don't reference citation indices. Anyway, so let's say we'll follow the ideas we developed last time, and we'll try to build to build a system that iteratively updates. So the idea is the following. Let's say we have a particular node, and let's say node 11 in this case, and we look at the rank of that node. Well, the rank of that node we will calculate it as a sum of the ranks of its neighboring nodes, but only those that are pointing to node 11. So that's where it's important that the graph is directed. Okay, so nodes 2, 10, and 7 do not endorse node 11. It's nodes 5 and 9 that have edges towards node 11. And so we can say the rank of node 11 is equal to the ranks of node 5 plus rank of node 9. Now, you can write summation over nearest neighbors, or you can just replace by summation of all indices. So j goes from node 1 to node n, but use matrix, and in this case it will be just binary matrix of zeros and ones to describe the connectivity pattern. And in our case here, we'll have a matrix A, and it will have, if there is a row 5 and column 11, somewhere on the 5 and 11 will be non-zero, and on the 9 and 11 will be non-zero element. And so please note that here it says AJI RJ, not AIJ, as we used to. Well, the reason for that is because since we're computing the rank of the node I, we need to take the neighboring node J, and the elements of the matrix that goes from node J to node I. And that's why it's AJI. So when we decide to write this in a vector form, this sort of inverted notation will really mean that you do not just do, if we consider R as a column vector, so our ranking is a vector where every element corresponds to one node in the graph, then we need to do A transpose R when we calculate the product. And A transpose, again, comes from the fact that when we do these computations, we need to multiply for every I, we need to get the incoming links. All right? Okay, so we can try to just, having introduced this type of, of updates, we can try to calculate these updates iteratively. So we can start with some particular distribution of ranks over all the nodes, which means, at time equal to 0, we assign certain ranks, certain values to each and every node. And then we start iterating, which means on every time step, we will update the value of the nodes based on the values of the nodes that are pointing to it. Now, there are some problems with this approach. So what do you think the problems would be?
All the values will float to that end.
I'm sorry, say it again?
The problem is in that end.
Okay, yeah, so there are actually several types of problems we're going to be facing here. So one problem is, well, okay, the most trivial problem will be actually here. If there are some nodes that are pointing to your node, then taking into account that matrix A is binary matrix, so it is elements are zeros and ones, are greater or equal than 0, then when we multiply them, the scale, the length of vector R will increase. So first of all, we're going to get sort of increase of those values for some of the values. For others, we'll get into troubles because there is no rank coming into it. So they don't have neighbors. And if we try to re-rank them based on the rank of incoming of other nodes surrounding it will get zeros because node 5 doesn't have incoming links. So just as is, this process will not work. Now, if matrix A was symmetric, which means the graph was undirected, this process would work. And the only trouble we would have is this with increasing of the length of vector R. But we know how to deal with that. We'll just introduce some sort of damping factor here, right? We'll just damp it somehow a little bit, and the way we did for the cat centrality, and that would work. Here, there are more troubles than that. In fact, there are 3 types of troubles here. So for iterative process, one is, as we described, there are source nodes. Those nodes that do not have any links coming into them. And even if we put some initial rank or initial weight on those nodes, in process of iterations, it will be zeroed out. But there are other type of nodes that are also troubling. These nodes, absorbing nodes. What in fact is going to happen is all rank, if you think about this rank, will flow into those nodes and accumulate in those nodes. These are absorbing nodes. And we'll see in the second sort of intuition why it's going to be happening that way. But you just can think about this as, again, you have certain nodes that do not have any incoming links, and then when you multiply matrix by the vector, they will be zero out. But there are other nodes that do not have outgoing links, and so they will accumulate sort of the values. And there is a third trouble, and the third trouble are cycles. So if you look here, and this is actually extremely problematic graph. If you look at these 3 guys, well, there is a cycle, and there is a cycle of length 3. Now, why cycle is a problem? Let me give you a very, very simple example. Let's look at 2 nodes. Okay, node 1 and node 2. And let them be connected this way. The matrix, the adjacency matrix that corresponds to this picture is 0, 1, 1, 0. Let's say we have initially distribution of the weight is 1 and 0, so the vector is 1, 0. And let's try to iterate. To iterate, what we're going to do is we're going to multiply the transpose of this matrix, which is itself in this case, by this vector. And what do we get? We get the vector 0, 1. So what happens, and if I multiply one more time, I get vector 1, 0. So we're going to have iterating vectors 1, 0, 0, 1, 1, 0, 0, 1, etc. So this process, iterative process, will never converge. What's going to be happening is, the rank will go from one node to another node and then back, etc., etc., etc. So it will not converge to any stable configuration. That's why cycles are bad. If you want to do any iterative algorithm, you need your graph or sort of the connectivity pattern to be acyclic. So these are 3 sort of fundamental technical problems. It's kind of also interesting to note that though last time when we talked about Katz's score or Katz's centrality, for simplicity, we discussed the symmetric matrix. In fact, Katz in his paper, original paper, he talked about Directed graph. But any directed graph will immediately bring you these troubles if you're not careful. So you either need to have a strongly connected graph and a cyclic graph, right? If the graph is strongly connected, which means you can get from any node to every other node, you will not have issues with absorbing nodes or source nodes, right? Because you can get from any node to any other node. You might still have cycles, but there are ways to sort of, fix that. Now, guys who worked on social network analysis, Leo Katz and others, they were not very much concerned about this situation because in social networks, they often talked about relationships, and if someone knows someone, well, that person knows quite often knows that person too. And if we talk about endorsement, like by people endorsement, well, it's very rare that you will see. If you see that somebody is being endorsed, but he did not endorse anyone else in the group, which means a situation like that. On top of it, since in social settings, these events are not very often, and social graphs back in the days in the 50s were not very large. They were all coming from sort of the questionnaire people filled. That was not a big deal. We'll see a little later that it is a very big deal for the web graph. And you can realize this, if you ever, looked, well, of course, you looked at the web and you realize that there are quite a few pages that do not have any outgoing links. Or there were lots of pages that do not have any incoming links. So for general ranking on graphs, this is very, very important. And so you have to somehow deal with it. If you do not do it, your algorithm just, if graph has cycles, it will not converge. If it doesn't have cycles but have absorbing nodes, all the rank will go and accumulate on those nodes. And pretty much all the source nodes will have 0 rank left for them. Okay, so these are sort of all the troubles you can get into if we just look at the graph and try to introduce this iterative sort of reinforcing procedure where it sort of connect the ranking and so the ranking on the node will depend on the ranks of the nodes that points to. In order to make this work, you need to do a lot of fixing with the graph. And surprisingly, well, actually, interestingly enough, Green and Page in their paper, they did all that fixing. They never talked about that fixing, but they introduced a method that actually implicitly solves this problem. And that's what we're going to talk about today. So, PageRank. This is actually a quote from their paper. They tried to model PageRank as a user behavior on the network. So they thought about a user as a sort of random surfer who is given initially some web page at random, and there are sort of procedures he can possibly do. One is keep click on the links. So look at the web page and go into the next page that is linked to this one, and just keep doing it. Or at some moment the person gets bored and just goes somewhere else on the web. Or if there is no outgoing links, well, he or she just goes somewhere else on the web. I mean, in some sense, again, these days with the search engines everywhere, the behavior actually changed. So you quite often just search the web, go to the web page you need, maybe browse that particular site you got to, but you rarely just sort of browse the web in its entirety. But back in the days, that was the sort of the surfing model, exploratory model. In fact, quite a few people do this today with social networks, when the people go to some profile and then follow some friends, and then look at them and follow the friends of friends, and then friends of friends of friends, and end up who knows where, right? So in some sense, this is very, very similar behavior. So this behavior is outlined right now on this picture with the following idea. So you have A, B, C, D, E are those web pages, and the gray links are those links that exist on the pages. Now, the red links is those virtual links that you add to this graph, those links that the person actually follows. So together, gray and red links allows the person to either follow the actual links or just sort of randomly jump to any other page. Now here we also get loops, which means you can reload the page or just stay in the page infinitely long. So this is a sort of random walker behavior, and I would say the main contribution from the PageRank was this idea that in order to rank pages, we will not think about just endorsement. We'll think about a random walk on those pages, in between pages, and the probability of this random walker to visit a page is proportional to the PageRank. I can say it differently. I can say, okay, if somebody is, walks long enough on this graph and visits different pages, and then you count the frequency with which the person visited pages, that frequency, later on, like relative frequency, will be proportional to the importance of those pages. Well, another analogy would be if you're in a big city and you're just walking the city, and you can take on every corner, you can pretty much, go left, right. To make complete analogy with web graph, think about, maybe one street, sort of one-way streets in the city. But the point is, if you do this a lot, you will eventually start noticing that certain squares, certain corners, you kind of see over and over and over again. It's just the structure of the city, of the layout of the city is such that with a higher probability you end up on the certain squares, on certain corners of the street of the city. From the perspective of the PageRank, it really means that those squares and corners will have a higher rank. So it have a high probability that a random walker, random surfer, visit the page. Okay? So the key here is a random walk. A random walk on graph. Now, if we think about it that way, there were a couple of things, there were a couple of improvements we need to do. And here is the formula again from their paper. I actually strongly recommend you guys to take a look at their paper. It's just quite interesting and amazing. It's written when Brian and Paige were like 21, 22, maybe 23. I don't know. I don't remember. Where Google is today, and that's probably it was pretty much the first and only paper of them together, I think. Anyway, so the probability, the PageRank score of node A has two parts, consists of two parts. One part comes from this accumulation of the scores from different pages. Let's look at this. Say we take we look at this guy. So the probability to be on this page comes from the probability to be on its neighbor, and this is, say, this neighbor. Now, when you're on that neighbor, you can actually go and visit different pages, right? So this is node A, this is node C. There is a connection, but you can also go from node C to node D and node B. And so if you're on this node C, the probability that you will be on the node A on the next step is actually the probability that you're not on the node C times the probability that you actually follow this link. But if there are 3, or in this case, I draw 4 outgoing links, then the probability that you will follow one of them is 1/4. And so that's why it's a random surfer model. So you randomly select one of the links and follow it. So in order to calculate the probability that someone ends up on the page A, you take the probability that the person, in this case, is on its neighbor from which it can get to A. But in any case, in any time, you have to divide it by the number of outgoing links from that page, because that will sort of renormalize and give you the probability to go to the node A. And that's what's in here, right? But that's not all. So that is sort of the first part, and this part is just tells us about the random walk. Now, there is a trick here, and the trick here about this virtual transitions. And what it says is the following. If you're on any node, there is a, and here they use D as a coefficient, right? So within that probability, you can actually follow that route, but there is 1 minus D probability to just randomly jump from any page to any page. And so PageRank of the node A comes from 2 factors, right? One factor is this little probability that the surfer will be anywhere on the graph and just jumps to it. And there is this part of the probability that comes from surfer coming from the nearest neighbors. So again, there are 2 pieces. One piece is just following the links, the edges in the graph, and follow according to the rules of probability, so doing random walk. And second is having this virtual jumps. Well, in fact, this second term with virtual jumps, with sort of going to any other page on the graph, that trick, in fact, fixes the problems with graph, the problems we had with source nodes and sync nodes. We'll see how. Actually, yeah. So it fixes it because, for example, if we had a node like on this picture, original node A, and they didn't have incoming links, well, there are virtual links, red links that comes into it. And if it didn't have any neighbors for people to visit it, well, there is a sort of virtual neighbors from the red links. The same with absorbing nodes. If there is an absorbing node and there were any edges leaving it, well, now there are virtual edges. It just means when somebody gets there, well, there is this probability to get out. So that's sort of the big picture and the idea. And in fact, this is the only formula that were in that paper. But the idea of the random walk, of actually measuring the importance of node by random walk, I think that is the key to this whole thing. Well, in fact, the second you say random walk and probability, you instantaneously get yourself into the Markov chain fields, right? You realize that this is a Markov chain, and what you're looking for is their is a stable distribution on the Markov chain model. And there are tons and tons of mathematics that tells you how to handle the graphs if you want, if the graph represents Markov chain. Again, the words Markov chain were not used in the paper. So it's kind of amazing. In the PageRank paper, they didn't refer to this whole literature on analysis from the social studies, on ranks, on prestige and centrality, and they did not refer to sort of Markov chains. But arguably, at this moment, the PageRank paper and model has a tremendous effect, and definitely much higher effect, much bigger effect than, say, papers by Katz or other sociologists. Okay. So now we understand that it's a random walk on the graph, and let's for a second, again, forget about the sort of the troubles we can get because of absorbing nodes. Let's just look at some nice graph where there is no absorbing nodes, and we can actually looking at the random walk. Here I do not. Here I sort of do not separate. I do not add the sort of virtual links. Let's say our graph is already sort of nicely connected, and if you look at this, it is a strongly connected graph. You can get from any node to any node on this graph, or you can also think that, yeah, well, we added this part of this virtual node of virtual edges here. So mathematically, what do we do? Well, we define now rank as a probability of being at the node at the moment of times, right? So for every node, we assign pi. And that probability, and again, we're not looking at the virtual sort of edges right now. The probability comes from the neighborhood of the node, and the neighborhood is a probability to be on probability to be on those neighbors at time t. But now we need to divide it by our degree of the node, because again, if I want to calculate, PageRank or rank for the node 2, the probability to be on the node 2, I need to take into account probability to be on the node 1 on the previous moment of time and probability to be on the node 4, because these are two nodes that coming into node 2. But if I'm on 4, I actually have 3 ways to go. I can go to node 3, I can go to node 5, or I can go to node 2. So the probability that it will end up on the node 2 starting from node 4 is probability of being on node 4 divided by 3, which is our degree of the node. Okay, and taking into account the connectivity pattern, the connectivity adjacency matrix, you can write it the following way, where dj out is our degree of the node. So if this is a matrix, to calculate the out degrees for every node, we just sum across the matrix, across the line of the matrix. Okay, that will give us our degrees. Now, there is a convenient way to write this in matrix notation. If we introduce matrix D, which is matrix that consists of just diagonal elements, and on the diagonal there will be no degree out degrees of the nodes. So matrix D is diagonal, where here we have our degrees for the nodes. Then we can write down this equation in the following fashion. We can write it d minus 1 times a, and again, in this picture, we do not have absorbing nodes, and so we do not have a situation where the row of the matrix is just consists out of zeros. Remember, for example, if we had a node that is absorbing, it means it doesn't have out degrees. It means that the row of the matrix for that node is 0. So again, let's assume for a second that we don't have those nodes. We'll fix them later. So if we do not, you can write this degree matrix, and then you can of course calculate inverse of that matrix. Well, inverse of the diagonal matrix is just the matrix itself with inverse of every diagonal element. So you can write it that way. So it is d minus 1a. Again, it's transposed because of the way we have indices here. And then you can write the transition as p transpose at p at time moment t plus 1 is p at times t times this transition matrix. And as again for p, we use column vector. Well, in fact, this matrix is called a transition matrix, and it's Markov chain transition matrix. And in the theory of Markov chains, it's been shown that there exists a limit under certain conditions, and we'll look at those conditions in a second. But under those conditions, there is a limit of this p to t at time goes to infinity, and there is a stable distribution or limiting distribution of the Markov chain. So which means that those iterations will converge to some probability distribution that doesn't change with time. And that probability distribution is your PageRank score. Now, since it's a probability distribution, of course, it has to satisfy this constraint that the total sum of all values is equal to 1. Okay, so there is direct connection. This is direct connection between PageRank and random walks on graph and Markov chains. So what are the conditions under which there exists this limit? Well, they're actually well known. In fact, those conditions were given originally by Perron and Frobenius at the beginning of the century. It's called Perron-Frobenius theorem if it deals with general matrices. If we talk about the Markov chain matrix, then it's called fundamental theorem of Markov chains. So if our matrix is stochastic, which means it describes Markov chain, and the matrix is non-negative, very important. And if it describes Markov chain, it's transition probabilities. And rows sums up to 1. Then it's called stochastic matrix. And in our case, it is a stochastic matrix because, remember, we normalizes the rows by out degrees. So that makes them sum to 1. Now, if the matrix is irreducible in the terms of the graph, it means that the graph is strongly connected, or from every node you can get to any other node. And if the graph is aperiodic, or matrix as aperiodic, then the Perron-Frobenius theorem tells us that this limit exists. And what's very important, it can be found as a solution of eigenvector problem. So it's an eigenvector problem where largest eigenvalue, lambda, is equal to 1. And it can be solved. And P is a stationary distribution of Markov chain. Now, notice that here I use very, very standard for Markov chain theory notation of vector P being raw vector. And that's why I put here this horizontal line, just to remind you that it is a raw vector. So if it's a raw, it's a left eigenvector. You multiply on the transition matrix from the left. If we wanted to write the same equation for the column vector, well, we just transpose this equation, and we'll have P transpose times P equal to P, right? And again, I explicitly show here that P is a column vector. Now, traditionally in linear algebra, people use column vectors when they write equations. And that's why we sort of drag along the transpose here to be able to use column vectors and multiplication on the right. But of course, you can write this equation with vectors that are rows, and then it's going to be left eigenvectors and left eigenvalues. But of course, for us, it is the same, just a matter of notation. Now, the key here is because of the Perron-Frobenius theorem, in order for our random walk to have a limiting stationary distribution, the graph on which we do the walk should be strongly connected and should be aperiodic. And if you remember just for a sec what PageRank proposed, it was the idea of adding this virtual links that connects every node to every other node. But by doing so, they modified a graph to be strongly connected. Periodicity is, it's an interesting condition. We saw it on a small graph that it's a very brittle condition. It can be destroyed very easily. And on the previous picture, it was destroyed, for example, because nodes have self loops. But in large graphs, it's very rare where you have periodic graph. So that's really not a problem. The main problem is reducibility, sinks, and sources. And that's being removed by PageRank by introducing those virtual links that connects every node to every other node. So this is an insanely powerful idea to connect them just with a small weight. And by doing so, you know, the brilliant Page, they actually made WebGraph satisfy Perron-Frobenius theorem. Again, read the paper. There is not a single word about Markov chain, about Perron-Frobenius theorem in the paper or anything like that. They just showed that if they play this trick, and the trick comes from this notion of, you know, random surfer, then, you know, miraculously things work out. You know, later on, when Google became Google, and people start looking into why algorithm works, a lot of mathematicians start looking, they realize, oh, well, you know, this is really random walk on graph, this is Markov chains, and this is Perron-Frobenius theorem that guarantees it, and the conditions for the theorem is satisfied because of those sort of added virtual links. Okay, so that's pretty much this is the big picture of the story. So, in order to actually do the PageRank, you know, for real, we need to do several things, right? First of all, we have our adjacency matrix A, right? And let's say, you know, this is our bed matrix with absorbing nodes and with sources nodes, etc. So first of all, we need to create from that transition matrix. So the matrix that describes probabilities, right? Because this is a matrix of connections. Now we're going to talk about Markov chains or random walks. So we need a matrix that describes probabilities. It's of course the same matrix structurally, but instead of zeros and ones that are the weights, right? This is just a binary, you know, adjacency, the binary matrix. We calculate the transition probability matrix by doing this. Okay. Now, there are nodes here, like this, and for those nodes, the matrix A in that particular row will have only zeros. So when we calculate this transition matrix, you know, we don't touch that row. We don't want to divide by 0. So we create a so-called indicator vector that tells us that this row has zeros, and we just do not divide by 0. But we cannot, you know, just leave it as that. Remember, you know, we need to do what we need to do is we need to create a strongly connected graph, right? So, and the first condition of the Markov of Perron-Frobenius theorem that we have a stochastic matrix, and stochastic matrix tells us that every row should sum to 1, and clearly this row does not sum to 1. So we need somehow to fix that. Well, there are two ways to fix it. One way is, you know, very simple way for this type of absorbing node. We can, you know, add just a self loop, and adding a self loop really puts on a diagonal appropriate place on the diagonal. The matrix will put 1 instead of 0. That's one way of fixing it. Another way of fixing it, which is sort of more, you know, it's used more, it's more traditional, is just by adding to this particular node random. So by allowing this virtual links from this node to every other node in the graph. Okay. Now, it's very important to realize that what we're doing is creating virtual edges. You're not actually building this and modifying the matrix itself. You do not, because this matrix can have you know, millions and millions of rows and columns, and you do not want to create a row that consists of like totally, you know, row of ones, because here if I connect this node to every other node in the graph, it really means I modified my matrix by creating, row ones. I don't want to store that row. So that's why it's virtual. Okay, but it's not only that. So I need to create those rows, and I need to make sure that the matrix is stochastic. So in this case, if I want this to be to become transition matrix, it's not. I don't add just ones. I need to normalize this and normalize by out degrees. So when I'll talk about transitions, this is going to be elements 1 over n, 1 over n, 1 over n, etc. So the way to write it is the following. We take our transition matrix and we improve it, well, writing this P prime matrix by taking this matrix and adding for those nodes that do not have out degrees, or for those nodes that in the matrix has zero rows, for those 0 rows, we modify them by adding 1 over n. And S is an indicator vector. And if you think about this, what's written here in terms of sort of vector notation is we have vector S, and we have vector of ones, and E is usual notation for vector of ones. And when we do this multiplication, it's an outer product. So we create a matrix. That matrix has zeros everywhere, except the particular rows where S is non-zero. Don't remember that, and try to multiply the vectors that way. So what I'm doing here is I'm taking vector, like say 0, 1, 0, and I'm multiplying by this vector 1, 1, 1. Okay, and you realize when you do this, you will get a matrix of 0, 0, 0, 1, 1, 1, 0, 0, 0. So it will actually do what we wanted, right? And divided by n, well, it's going to be here then matrix 1/3, 1/3, and 1/3. So by doing this trick, I'll fix, and my P prime matrix will be stochastic. So this trick fixes nodes with 0 out degree. And then I'll actually create a PageRank matrix out of it, or sometimes this is called the Google matrix, where I take this matrix and now add the random transition to every node, from every node to every node, with a smaller probability. And E transpose is really means, again, you take a vector of all ones, you multiply it by vector of all ones, that will be matrix of all ones, which corresponds to a transition from every node to every node. Now, again, this is a notation. You don't want to do it. You do not want to actually create this matrix. So as a result, what's going to be happening is the following. By doing this, we added to every node, transition to every other node. And for those nodes that were sync nodes, like node number 2, for them there is no other way to transition out than just by jumping. So for them, these virtual transitions will have a probability 1. For other nodes, the virtual transition will carry the weight, or probability 1 minus alpha. And so this virtual links will go here, and for this node, it will go to every other node. And for this node, it will go to every other node, and et cetera, et cetera, et cetera, et cetera. So this is going to look like a complete mess, right? But it will guarantee that the graph becomes strongly connected. And that's what we need. So now we have a stochastic matrix, and it is strongly connected, and it's acyclic. As a result, it's guaranteed that this eigenvalue problem will have a solution with eigenvalue 1, and that vector will be, actually, I didn't say in the previous page, but Perron-Frobenius theorem tells us that, first of all, this eigenvector, the vector P, will be non-negative. So all elements will be non-negative. And the solution will be unique. Now, it's very important that it is, well, first of all, it's unique, which means, if you do ranking, it's unique ranking. It doesn't matter from which sort of initial conditions you started. When you do iterations, you will converge always to the same solution. If it was not unique, it would make sense. The second fact that the vector will actually have all the elements. There will be probabilities. They will be greater or equal than 0. It's also not trivial. The fact that they're real and greater or equal than 0. Because if you think about it, the original matrix we started and the transition matrix is not symmetric. And we know that for non-symmetric matrices, typically eigenvalues and eigenvectors will be complex numbers, right? It's only for symmetric matrices they're real. Well, the stochastic matrix is a very special matrix, and for that one, for strongly connected stochastic matrix, they are actually real, and they're greater or equal than 0, and they're probabilities. Okay, so again, just to reiterate, it's a random walk-on graph, and by introducing these virtual links and virtual connections, Brin and Page solved the conditions for Perron-Frobenius theorem that guarantees the convergence and the existence of the solution, the uniqueness of the solution, and the convergence of the solution by iterative procedure. Without saying a word about it. So, the reason I kept insisting on just sort of writing the matrix, but not thinking about modifying the matrix by writing the equation, but not modifying the matrix is the following. So here is that piece of that equation that we just had, where this is a sort of Google or PageRank matrix, and this is our condition. Now, if you multiply through, then we take this, multiply by this, we got this guy. But what happens if we do multiplication E transpose times P? Well, in this product, you can actually use association rules and multiply this part first. Well, what's E transpose times P? Well, E is bunch of ones, and P is our vector of probabilities. Well, this multiplication, this product, is really just the sum of elements of the vector P. So E transpose times P is really just sum of all elements of vector P. But these elements are probabilities, so they sum up to 1. Okay, so this is just a norm of vector P, which is 1, and that's why when you multiply this through, it actually goes away. And so we get the formula for power iterations. Now, I strongly recommend you to look again back into the equations by Leo Katz, about the prestige in social network. And in fact, if you don't want to dig and look in his papers, take a look at network X definition of Katz centrality. And you'll see the formula very, very much similar to this one, with some differences, and the difference would be that here we're actually dealing with transition matrix probabilities. Over there, it would be just an adjacency matrix. But you will see that this similar structure. So one more time, in order to calculate PageRank, we can do this power iterations. We start with some P, which can be a initial random assignment of weights on every node. We calculate this P prime matrix, and this is a matrix. It's adjacency matrix normalized to out degrees, and where 0 rows replaced by this 1 over n thing. And we add we use this parameter alpha. And this parameter alpha it's called teleportation coefficient. It controls on how much in this process we actually follow the links, the real links, because this is following the real links. And this is jumps using virtual link. Well, Google by itself claims to use alpha to be 0.85, right? So it's 85% following the real links and 15% doing random hops. You can also realize by looking at this that alpha as a parameter will control the convergence of the algorithm. Think about this for a second. Imagine that we decided to use alpha equal to 0, which means that we're not using the real links and we're only going across, we're only doing virtual links. Well, virtual links, they connect every node, to every node. So there is a direct path from every node to every node. And when you start updating this kind of system, it's one step to update all the nodes. And that means that the system will converge very, very quickly. If we reduce that or go to increase alpha, we're going to lose the convergence. If we go and take alpha equal to 1, will actually means we're not using any virtual terms, virtual edges. Then most likely the iterations will not converge, simply because the original matrix is not, the graph is not strongly connected. And so this adds strong connections, but puts the small weight on that strong connectivity. So it allows to converge, but controls conversion. It's also, we should also realize that if we use if we take alpha to be very, very small, which means put a lot of weight on this, we're sort of destroying the structure of the graph, because we're connecting everybody to everybody and we're letting everybody jumps all the time. So there is a delicate balance in the selection of alpha. And of course, when you change alpha, you change ranking. So in some sense, it will be fair to write that it's P of alpha, right? With different values of alpha, you'll get different page ranks. Now, another way to look at this equation, if you look here, you can actually take this, take it on the left side of the equation and write it as a linear system. Now, if you remember a little bit of linear algebra, then you realize that, okay, well, this, there is non-zero right-hand side. If we take alpha equal to 1, it's going to be 0 right-hand side, right? If it's not, here is a matrix. And depending on alpha, we have different matrices. And so this matrix will have different condition numbers. And condition numbers dictate the convergence of iterative process when you do solve linear systems. So alpha is a parameter, the teleportation parameter. On one hand, it controls the structure of the matrix and how much influence we put on the random hops, jumps. On the other hand, it controls the convergence of the process. So again, the Google itself has selected these values. You make it lower convergence will be better, other way around. Okay. So why bother? I mean, there is this whole mathematics, and we did a lot of computations to handle, to deal with this absorbing nodes and to deal with sources. Why can't we just ignore them? I mean, you can actually generate strongly connected graph. Say here is, we have some strongly connected graph by we can cut out those guys, for example. Just cut them out, and work only with a strongly connected component. And actually, that's one of the ways to deal with it. Now, the trouble with this approach is the following. The trouble is in the number of pages that are actually either source pages or sync pages. This is a very, very influential paper by Andre Broder from IBM, circa 1999. They used one of the first publicly available crawls of the web from Alta Vista, which had like, I think, a couple billion pages back then. And they, in fact, calculated how many of those pages belong to different components, right? And the top picture is pretty much from the paper. The bottom one is a little bit of explanation what it means. And so they defined the web graph to consist of several parts. So there's a central core that contains, if you look at this, probably half or 40% of the nodes. And this is a strongly connected component in that part where every node is connected to every other node. Then there is what they called in nodes. These are those nodes that are connected to strongly connected components. So if you start from those pages, you can get into this strongly connected component, but you cannot get out. And there is another type of pages and links where you can come to them from strongly connected component, but you cannot get back to the strongly connected component. So if you decide, by whatever reason, not use a PageRank as is, but just work on a strongly connected component, you will be stuck with less than half of the web graph, and you'll have to deal somehow with the rest of the pages. And I mean, people try to do that. Now, there are other type of nodes. Again, take a look at this picture carefully. You realize that there are some connections from here to there, and there is called tendrils. The paper is very short, but actually very, very interesting. So first of all, they talk about, and they call this a bow tie structure because, the way they draw the picture, it looks like a bow tie. So they, first of all, they looked at this structure, and they also did their sort of the famous power law graphs, where they looked at the node degrees and how many nodes have those degrees. So it's a very, very influential paper. If you're interested, take a look at it. So that's why PageRank is so important, because on the web, there's at least half of the pages that are either that are out of the strongly connected component. Again, this is circa 2000, so at that time there were in this particular crawl, you can calculate how many pages. There was probably 200 million or something overall, but it's clear that with web graph growing, the proportion might shift, but not dramatically. And so that's why it's just the PageRank is a PageRank. Okay. We have a couple of minutes left. Let's talk about a little bit different way to rank pages. And this algorithm is called hubs and authorities, or HITs. It's really comes from the idea of citation networks. And the idea is the following. It's actually proposed by John Clyburn pretty much the same time as PageRank. And the idea is the following. You might realize, and let's for a second think about, again, scientific citation and research papers. There are certain papers that everybody cites. And these papers, they're usually very authoritative papers. So they might contain, some sort of, great new discovery or written by famous people. It's like this PageRank paper, right? So this paper, very authoritative paper. It has high authority. It's being cited by a lot of papers. I'll put it A, because authoritative. But there are other papers, like reviews, that actually cite that their goal is to be connector in this world, right? To cite other papers. They're hubs. And the idea is the following. In the real world, there is no pure authorities and there is no pure hubs, but one of the other will dominate in the sense that, yes, authoritative paper, though it is cited by lots of other papers, it still cite some papers in their research. And the hub, though the main role of the review of overview paper, sort of review paper, is to cite other papers and collect the knowledge. Well, there will be more papers appearing that will cite the review. So both authoritative papers, pages or papers, and hubs will get incoming link and outgoing links. So for every paper, you can think of two scores: how much paper is authoritative and how much it's used as a hub. So and then there is a sort of idea, okay, well, if the review is good review should point to good papers. So the authority of the papers really depends on the authority of the reviews that points to that paper. And the other way around. A good hub, a good review, is the one that points to good papers. So let's think about this. If we introduce, for every node, we introduce, instead of one score, two scores. A, which will be authoritativeness of the paper, and H will be sort of hubness. Then good authorities, so the value of authority for the paper or for the node, will actually depend on the values of the hubness of their papers that points to it. And AGH is again just the connectivity matrix. At the same time, we can say that good hubs point to good authorities. So again, the same idea. Just take a look, notice this, the indices here. It's paper AI, and we take all the hubs, and now these hubs are pointing to AI. So the indices here, JI, so it's J points to I. Okay. This here, it's written sort of in inverted fashion. Again, this is, now we're talking about I pointing to J. This is a connectivity, AIJ. And so this is hubs pointing again to authority papers, but it's written in terms of hubs. You can think about it the following way. Imagine again that you have just sort of papers with a lot of hubs score, and we'll call them hubs, and we have authorities, and there's this connectivity pattern. So the authority gets their weights from hubs. Now, the reason we want to write this is because all of a sudden, if we have not one score, but two scores, well, we'll need two equations, to deal with them. And if we write this in vector notation, we'll get the following. It will be A will be A transpose times H, and H will be A times A. And we already talked previously that if we want this type of procedure to actually converge, if we want to iterate and come to some sort of stable solution here, we'll need to use some factors, alpha and beta, as a damping factors. Well, we can easily try. You can take this H and plug it in this equation, and then we'll get equation for A, or we can get take this A and plug it in this equation. We can get equation for H, or you can just iterate these equations, solving one then solving another. But the point is, what you're going to get is you have symmetric eigenvalue problem that calculates A and H. It's actually very cute in the sense that, yeah, you can, for every page in the graph, you will get 2 scores, N and H. All right, guys, I don't see your feed. Are you still there? All right. So this method does not, though it's kind of interesting and allows us to work on assigning and creating for every node 2 scores. I'm sorry, 2 scores, the authority score and hubness score. In practice, it doesn't work as well as PageRank. And in fact, the original design, the proposed by Kleinberg, was not using this scoring mechanism to score the entire PageRank. It was designed to do the following. It was designed to score focused subgraph. And the focused subgraph Kleinberg defined the following way: taking the search query, sending it to the search engine, getting search results, extracting connection between those pages, expanding a little bit of that set by adding to the pages in the set that came back from the search engine nodes one step out, and then computing hubs and authorities. It's sort of re-ranking in some sense, re-ranking on a smaller subset. And there were some search engines, I think AskJeeves was trying to use this as actually a ranking scheme. But again, it's sort of local. It was a local ranking.